Hi, everyone. So I'm Quinn. I drove up from San Diego last night instead of this morning after having learned to do that many, many times. So I'm so happy to be here. I love coming to the Sagan, and I hope you all had a wonderful week. So I was asked to discuss the potential for atmospheric characterization of exoplanets using the future extremely large telescope facilities that are being planned and, as Chaz says, in various stages of development at this point. I'm going to try to do my best to convey to you some really exciting things that we hope to do with these facilities in the future. Okay, all right. Okay, so one of the things I think that is important to keep in mind as we think about building these very large and very expensive telescopes is that as we've constructed new telescope technology over time, we've always found new and unexpected things that we didn't anticipate. So I want to go back even further in time than Nicole did to start us today. With the advent of the very first telescope, the one that dominated most of human history, which is this one. So this is where we started. Does anybody know how, if your eye was a telescope, how big it would be or how big it is? Are there like optical people who do eyes? That was really good. Yeah, I had no idea. Yes, 6 or 7 millimeters. So the first telescopes are 0.3 inches. And of course, we did wonderful things learning about, 6 planets in our solar system just using our eyes. But then, fast forward thousands of years into the future, and you finally get the development of the actual separate telescope from your eye. So this is Galileo's telescope that he developed after the invention of the telescope by Hans Lippershey in the early 1600s. And this was a major revolution, as we know, in science in general, just increasing by a little bit. So we've now gone up from 7 millimeters to 37 millimeters, or about 1.5 inches in size. And with this, he basically revolutionized science, as we know, but he also was able to make really important discoveries for planetary science. So that included this one, which I found this really fun video, where this artist took the actual images from Galileo's notebook and tried to match them up to what we would actually use in a real simulator today to see where the Galilean satellites would be. So this was done over the course of I think it was January to March in 1610 or so. So that was a huge breakthrough, obviously. So let's continue our journey in history and come forward in time from here. So next, we fast forward to let's talk about this guy. So this is famous astronomer William Herschel. He was really interested in cataloging the sky. So he started developing his own telescope technology. And this particular telescope, he had many, was one he developed to do a catalog of binary stars. So this is the one he used. And when he built this, was about, now we've gone up another factor of several. So now we're at 6.2 inches in size. And with this telescope, he discovered the first planet that we couldn't see with the naked eye, which was the Uranus, which he found in 1781. So that was another revolution, of course, because it just showed that our solar system was bigger than we actually thought it was, and was completely unexpected. He wrote down in his notebook that it was like a comet or something, which is pretty funny. And then we found out it was an actual planet. Okay, continuing forward in time. So let's keep building bigger and bigger telescopes as we are wont to do. So this is a telescope that was built in the mid 1800s by Fraunhofer, who was actually a glassmaker, even though he's famous for the spectral lines in the sun. And he made kind of the most amazing telescopes of the time. And so this one was given to the Berlin Royal Observatory. And it was 9 inches in size, so it was very revolutionary and one of the best telescopes in the world at the time. And this person, Johann Gottfried Galle, used it to discover Neptune. And now we're in 1846. So we're continuing, as we continue to grow our telescopes, we continue to get more and more discoveries. So now I'm going to fast forward through a whole bunch of time in which we know that the revolutions in astrophysics in general happened because of the development of additional large telescopes, to bring us back a little bit more to now. So in the modern era, it's not just necessarily just making the bigger and bigger telescopes. It was actually clever combinations of those telescopes with technology that have really led to the breakthroughs in exoplanet science, I would say. So does anyone know which telescope this is? If starting exoplanet talk, which planet do we always start with when we talk about exoplanets? Pluto? No, it's not. It's not the one that found Pluto. I know. I've gone now outside of the solar system. It's okay if you don't know. Hot Provence, yay! All right, yes, this is Hot Provence. The 1.93 meter telescope now are 76 inches, so I've gone to meters from millimeters now. So this was built and it's in France, and it was built in 1958. And of course, this is famous for using this kind of now much larger telescope, the 2-meter class telescope. But in conjunction, at the time in the 1990s, this wasn't the biggest telescope in the world anymore. But there was the use of it with the very, very precise LED spectrograph that could do precise radial velocities, and therefore allowed for the discovery of 51 Peg over the course of observations in 1994 and 1995. Okay, so now I would say that the important thing is to make sure to keep getting bigger, but also to think about your instruments that you're putting behind the telescopes too. Okay, so and people have continued to do that. So we've moved beyond the era of just individual discovery of planets into the era of large surveys that can really have led to these gigantic breakthroughs in our knowledge of exoplanet demographics, including things like the HARP spectrograph, which has now gotten to be up to the 3.6 meter telescope in La Silla, Chile. So we're into the 4 to 5 meter class regime now. And this is doing, is a much greater advancement beyond what LED was capable of, and is allowing us to do amazing science. And another telescope that was really important. I hope everybody knows what this one is. Kepler, yeah, it's in space. So hopefully that was a good clue. So here's a picture of Kepler. Kepler is famous for, I think it might be I'm at the place where people can correct me if I'm wrong. I think it's the one that discovered the most exoplanets. Is that right? Yes. Okay, good. Thank you, Chaz. So I was like, I don't think Tess has beat it. So Kepler is only a 1.4 meter telescope, so 55 inches, that operated, 2009 to 2018. And again, it wasn't a gigantic telescope, but it had very, very clever technology behind it. So the Kepler focal plane with this big 1 foot square, different combination of CCDs all piled together that allowed for very, very precise photometry was what made this combination so powerful. So it's been, not necessarily always about getting bigger in aperture, but also getting clever with your instrumentation. Okay, so we've been hearing all about, exoplanets, there we go, over 2,600 exoplanets discovered. So those are the ones that are doing the large work for finding new planets in general with surveys. We've also I hope that you've seen a lot of interesting discoveries that have been done with the largest ground-based optical telescopes so far. And these are in the 8 to 10 meter class regime. So just to keep with my inches here. And these ones have been doing amazing science, like finding the first directly imaged planets around other stars, doing spectroscopy of fainter and fainter objects, et cetera. So we're in a really, really good place, and we're making really amazing discoveries. So the question that you might be asking is, if we're doing amazing things with, the 10 meter size telescopes, and now with JWST, which is less than 10 meters in size, why are we trying to even go bigger? And I'll just answer my own question, because I'm sure you all know the answer, but bigger telescopes have bigger sensitivity, right? And also greater spatial resolution. So we really want to take advantage of the combination of those two to push even further than we can with necessarily JWST and other facilities we have now. Okay, so notionally, you may recall that the telescope sensitivity and what you potentially learned in your intro astro classes just goes as the area of the primary mirror. So this is the typical picture that you'll see. You imagine your mirror as a bucket collecting rain. In this case, the rain is photons. And you immediately intuit that the bigger you make the surface area of the opening, the more raindrops or photons that you'll actually be collecting. So that means that we usually learn that the sensitivity of the telescope goes as the diameter squared, or as the area. But we also have to think about resolution. So sorry, I wanted to put how ugly, sometimes I forget how ugly the area pattern is. So I like to show the equation. So the resolution, as you get larger, in terms of your telescope size, also improves. So remember that what we're looking for here is when we do a cut across of what the diffraction pattern looks like, you'll see that you can compute at what point the first hole in your peak is, and that comes out to be where the sine of theta is equal to 1.22 times lambda over d, or your Rayleigh criterion. So because we want resolution or theta to be smaller to be able to resolve better and better things, we want bigger telescopes as well. So it goes as 1 over d. But it turns out that what we've all learned about in terms of the telescope size, the telescope sensitivity just going as d squared, is actually can be shown to go as d to the fourth if you also account for resolution. So the way that this works is when we're thinking about telescopes on the ground, we usually have to deal with the effect of the atmosphere. And what that means is that if you're not taking full advantage of your full aperture and reaching the diffraction limit, your PSF will be all smeared out over a lot of pixels. And that means as you try to integrate your whole signal, you're going to be combining a lot of background noise photons and other noise sources to try to incorporate the whole thing. Whereas if you reach the diffraction limit and shrink your point spread function down to a really nice little peak, like you can see right here in this image from, this is taken from simulations done with Keck. So what it looks like with no adaptive optics and what it looks like with adaptive optics or diffraction limited techniques. You get the tight peaking of the PSF, which means that your signal is in a lot less pixels, which means you're getting a lot less background integrated into your image. And if you do all the math, it comes out that sensitivity actually goes as d to the fourth. So it's a much function of the area of the telescope than we are previously kind of taught. Okay, so all together, you put all of these motivations, and that leads to the impetus for us to continue to push, especially towards larger and larger telescopes on the ground, where it's a little marginally cheaper and a little bit easier to build really big things. So this is the fun Wikipedia picture that shows like the compilation of all the different sizes of different telescopes that are available across both the ground and space. And so, because we're getting to the era of telescopes the size of places where we play sports, you have to have your tennis court and your basketball court on here for size comparison. I also sometimes get asked about the overwhelmingly large telescope, which is this thing behind. Some people may remember that was canceled, but they still put it on here. So the ones that we've been talking about for today are the ones that are kind of more on the left-hand side, and then the three giant segmented mirror telescopes, because they have to be basically just like JWST made up segments for them to be able to get this big. We can't make glass monolithically that can be supported for the sizes that we want. So the three of them that are planned are over here on the right hand side. So I'm going to talk about each of them individually. So first, let's see, we'll start with this one down here. So this is an artist rendition of what this looks like. So none of them are actually all the way built yet. Some of them are in construction, but none are finished. So all artist pictures when you see these. So this is GMT, or the Giant Magellan Telescope. So this one is planned to be 25.4 meters across. So it's a combination of 7, I think if I count properly, 8-meter size monolithic mirrors that are put together to make the one aperture that's 24 or 25.4 meters across. And this one is going to be in Chile on Las Campañas Mountain. Okay, coming back here, let's go up in size a little bit. So I'll come talk about this one. This is an artist rendition of the 30-meter telescope. So it's exactly what its name suggests, is 30 meters across, which is also, now we're almost to the 100-foot regime, which is kind of fun. This is going to be a Northern Hemisphere telescope. So the plan is either Mauna Kea in Hawaii or La Palma in the Canary Islands for this telescope. And then finally, coming back here again, let's look at this one, the one that's the biggest, that's actually real. So here's a picture of this one. It gives you a sense of scale. I like this picture because you see the little tiny humans next to it, and also the cool lasers coming up. So this is the extremely large telescope. So this one is 39.3 meters across, or now we're almost to 130 feet in diameter. So imagine where we started at 0.3 inches, and now we're up to 130 feet. I think that's a factor of a lot, which I can't do in my head. Might have been 4,000. I can't remember what I did on my calculator right now. And this one is going in Chile on Cerro Armazones. Okay. So the one thing I did want to mention is that I talked about adaptive optics, and hopefully you heard about that earlier in the week, about how important and critical that is for us to do any of the science that we want to do with these with the 8 to 10 meter telescopes. At this point, all of them have adaptive optics, but for the GSMTs, which is what I'm going to start calling them, because ELT is also a telescope, so I'll just use GSMT for all three of them. So you have to have adaptive optics on these telescopes to do pretty much anything that you want to, any of the science. So they all have first light adaptive optic systems planned. And I just really I like all these fun videos that people make kind of demonstrating how AO works. And this is from ESO. What they were showing you, and hopefully what you saw, was that the light from your beautiful galaxy gets distorted by the atmosphere. We're not in space like JWST, so we have to deal with it. You measure what the wavefront is doing using a guide scar in real time, and you correct for it using a deformable mirror and and get back your pristine image, theoretically. So the issue with adaptive optics for telescopes this size is that by the time, and this is just a schematic, but I'll go through that really quickly. The issue with telescopes this size is that by the time you get to a primary mirror that's the size of a tennis court, you're starting to sample a lot more atmosphere. So we can use just a single guide star to measure what the atmosphere is doing and what the wavefront looks like with the current 8 to 10 meter telescopes, but that's not going to work for a 30 meter class telescope. One of the ways this is demonstrated is for in this image here is using a picture showing you this is supposed to be a picture of the laser guide star. So a lot of the science, when you need a bright enough star next to your target, a lot of targets aren't bright enough. So you make an artificial star by shooting a laser into the sky that excites sodium atoms 90 kilometers above the surface. And the problem is that that's not at infinity, but the galaxy or whatever you're interested in is at infinity. So you get something that's called the cone effect, where the atmosphere that the light from the laser is passing through doesn't end up being the same atmosphere that the star at infinity is. So you get a bad correction. So that means that you actually have to map the atmosphere across the full aperture of the telescope in order to get this pristine, very, very exquisite spatial resolution we need to realize our sensitivity goals. So this is a complicated picture that just is supposed to briefly demonstrate how multi-conjugate adaptive optics is what all of these telescopes are going to use. They all have them planned for first light. And what this does is use multiple lasers. So that's why you're seeing all these, and I'll show another picture of all these multiple lasers shooting out of these telescopes, and multiple deformable mirrors conjugated to different levels of atmosphere. And then they're going to basically 3D reconstruct the full atmosphere above the telescope. So it's talking about the need for clever instrumentation in addition to big telescopes. This is a huge engineering problem that I'm really excited to see what comes of it, because people are doing amazing work on this. And people have already demonstrated this from the ground. So this is actually a real constellation of telescope space lasers from Gemini. So this was the GEMS multi-conjugate adaptive optic system. And you can see in comparison to the constellation over here of lasers that the GMT, for instance, will be using. Okay. And also to give you a sense of scale, in terms of the size of the instruments now, just to be able to work on these gigantic telescopes, the instruments tend to get gigantic as well. So this is a picture of a model of the TMT first light instrument called Nefarious. That's the first light adaptive optics system. So you get a sense, here's a person next to this blue box, which is all AO. And then the instruments themselves, the imagers and the spectrographs, are these little kind of tic-tac cylinders hanging off the side. For a sense of scale, it's the same size as a semi truck. So it's really big. Okay, lots of engineering going on here. Okay, so that's kind of an overview of how I think how the telescopes, what their properties are, and how we're going to achieve this really, really good resolution. So I want to spend the last few minutes just talking about some of the science that we imagine being able to do with the giant segmented mirror telescopes. Okay, so the main thing that is important to realize that is the niche that these telescopes fill in terms of planets is the ability to do both high contrast imaging at the insane spatial resolution that's allowed for a 30 meter class telescope, and also being able to do really, really high resolution spectroscopy. So we can break down the planet science in general in a bunch of different categories. We can do formation and evolution and looking at disks. We can do architectures by doing precise RVs like we've been doing previously on the 8 to 10 meter class telescopes. Comparative planetology is kind of where the atmospheres sit here, but also in terms of the search for life, we can possibly do some work there as well with the GSMTs. So one thing I also wanted to say is that when I'm talking about very, very high resolution spectroscopy, I'm talking about what hopefully you heard about earlier in the week, where we're getting to 30,000 to 100,000 spectral resolution. So this is a figure that was made by Bjorn Bennecke, where he made synthetic spectra consisting of just one single molecule. in a near infrared wavelength where a lot of the instruments will operate for these telescopes. So between 1.4 and 2.4 microns, some of the molecular species that you've been hearing about already in the talks today. And if you do a comparison by zooming in really, really close on like a tiny, tiny little fraction of that wavelength regime, you see what a spectrum from JWST would look like. And I love JWST and I love the spectra. So just want to say that. But like how much more information you get at an R of 100,000 just in comparison. So the need for the sensitivity of these telescopes to do this enables that type of science where you can yield information that's complementary and also adds pieces to this puzzle that we're trying to put together for exoplanet atmospheres. So we're going to do unresolved science. So we were just talking about the cross-correlation technique and how that works really, really nicely for planets right now that are not resolved from their host stars. So even though we have this amazing resolution, some of the planets will not be resolved still, even with the 30-meter class telescope. But we can still do really interesting things with just having the high resolution spectroscopy. So what you're seeing here is hopefully something that you saw earlier. But what this represents is trying to figure out just by cross-correlating an atmosphere model template with really, really precise high signal to noise spectra, and trying to see if you can tease out the signal using the conglomeration of all of those amazing spectral lines. And they've demonstrated this a lot already with the 8 to 10 meter class telescope. So that's what's being shown here. The signal from HD 209458 with the VLT CRIRES, which is a high resolution spectrograph operating now. And just in comparison, how much cleaner you get when you do a signal using a 30-meter class telescope, because the sensitivity is just so much higher. So there's tons of different science you can do. You can do rotation of these planets. You can look for winds. You can do global circulation modeling, et cetera. All the amazing things that we've already been hearing about, we can do just at these very high spectral resolutions. Okay, this is another plot that was also made by Bjorn Benecke, who makes amazing plots. So what he was showing here was just taking a sample of known planets now, and also potentially notional planets that are discovered in the future, looking at those as a function of planet radius, what targets are potentially viewable using a 30-meter class telescope and a high-resolution spectrograph. And you can see how many there are here, just in terms of this is a detection in transit, and this is a detection in secondary eclipse. So we can detect things spanning the full interesting range of parameter space in terms of radius, and also in terms of potential equilibrium temperature as well. So what this is meant to convey is not for you to read every single one, but just that we can do a lot. We actually can see many of them. Okay. But coming back to direct imaging, which is my favorite topic. So again, they will have unprecedented spatial resolution. So that's going to allow us to get down to really, really tight separations well into the regime of the solar system planets. And this was a simulation that was done for the ELT METIS instrument, which is one of their high contrast imagers that they have planned for the European ELT. And so what they envisioned here was if you could have one Jupiter mass planet orbiting a sun-like star, could you see that with METIS? And the answer is yes, you can see it very easily. So this is a type of parameter space that's completely inaccessible to us now, and also is inaccessible to even the 6 meter telescopes in space. Okay. Can't have a talk without showing a Jason movie. So this is a movie that Jason made showing the orbit of 51 Erie, which is still, I think it's still among the smallest, if not the smallest directly imaged planet that's been seen in terms of mass. And what he did here was show what we can see now with high contrast imagers like the Gemini Planet Imager, and then fast forward in future to when maybe something like TMT Nefarious is in operation, how we can probe closer in these already known planetary systems. And what we've been finding is that looking at places where planets have already been found is like a really, really good place to look, unsurprisingly. So just how much you can see, even with just kind of the first light Nefarious AO system, which isn't even optimized for high contrast imaging, how well you can do. Okay. Here, I'll skip that because I'm running out of time. Here's another really cool thing that I wanted to talk about. So the GSMTs are going to be able to image hundreds of exoplanets, including ones that are known from radial velocity techniques and ones that maybe we'll find in the future. What these folks did, looking into the future, what kinds of things we'll be able to detect with direct imaging, they created a notional population of planets that's plotted on here, and then they looked at the parameter space that's accessible to these types of telescopes. That's kind of up here at wider separations. And then this is contrast, which you've seen before. And then this demonstrates the equilibrium temperature. And what they've done is estimate which types of objects we'll be able to see, and noted that if you have the right instrumentation suite that can do reflected light imaging, but also thermal imaging, I'll stop in a second, you can do both reflected light and thermal light. Allows you to get the entire energy budget of the planet, which is really cool. So we can do that too. All right, I'm almost done, I swear. I'll just fast forward through that. We saw this earlier, so I wanted to just end really quickly on the fact that even though a lot of the work on biosignatures and technosignatures also will be done from space, the ground-based telescopes, and especially these really large ones, will be able to contribute to this because we'll have wavelength sensitivity in these regions. And people have done a lot of work exploring what would it take to detect something like an oxygen feature from a ground-based extremely large telescope. And it turns out you can actually do it. So this work from Snell et al. In 2013 tried to figure out how many transits you would need to look at using the cross correlation technique to see the O2 band here at 0.76 microns. And it turns out you can do it around a nearby M5 star in 30 transits. So he was able to show that you could detect that. And then we saw this plot already, but I really like it. It just came out showing all the different types of atmospheres that Eddie talked about this morning, and how many transits you would need to be able to see a whole bunch of different potential signatures of biotic life. And then in fact, it's not that many, and we can definitely do it from the ground. Okay. Almost done. So just the last thing I wanted to say is I found there's a whole bunch of different instruments that are planned for these telescopes. I didn't talk about them at all because there's not enough time. But if you want, you can check out at least some of these. These are kind of the high resolution near infrared spectrographs that are being planned to be coupled to adaptive optics. So there'll be a lot of the workhorse in the near term. And so I just wanted to leave you with, I hope that it's not actually that far off that we're going to be starting to see these telescopes come online in the next 10 years. So I think we're going to be seeing some really, really exciting stuff by the end of the decade. And I look forward to it. So thank you very much for your time.
Great, thank you, Quinn. Any questions first in the room? Yeah, one.
Hi, great talk. My question is, so currently there are about like a dozen 8 to 10 meter class ground-based telescope, but only about maybe 2.5 30-meter telescope going to be coming online. So do you think that means there's much more room to build 30-meter telescopes by another factor of 5 more, or are we just going to put our resources into building a 100-meter telescope and call it good?
Question. These telescopes are really expensive. I mean, they're not like JWST expensive, but they're not like that far away. So they're in the, the low, like couple $1 billion range. And so that part alone kind of limits, I think, the available resources that we have to actually construct them. And so all of them, I didn't really mention, every single telescope is being conceived by a consortium of different countries. Basically, we're not talking about like individual institutions anymore. It's like the entire country of India, the entire country of Japan are contributing to these telescopes. So it would be awesome if we could build more, but I just don't think that we have probably the resources to do it. Yeah.
Hi, great talk. I was actually kind of curious, and I don't know if you would know the answer, why they chose circular mirrors instead of the hexagonal shape.
For GMT?
Yes.
There might be a different answer, but my understanding is because that's what they know how to make. Yeah, that's what they have a really amazing mirror making facility that they use to build these beautiful mirrors, and I think they decided just to put them together. Yeah, there's probably a smarter answer than that, but yeah.
Okay.